Hey everyone, welcome back to Math 256. This is Scott. Let's get started. So what we are going to be doing now is picking up where we left off and looking at the geometry of the eigenvector eigenvalue analysis that we did in the previous section. So what this is, it's section 3.3 and it calls itself the phase plane analysis of linear systems. All right. So first off, here's the setup. We're just going to have the same sort of system as what we had in the last section, and that's going to be just a system of two differential equations, both of which are going to be linear and homogeneous. So a system of the form dx dt is equal to ax, where A is just going to be a 2 by 2 matrix. Okay, so this is, although maybe sometimes the notation is a little different here and there, this is the same setup as what we've been dealing with. Okay, so first off, a note. So there will be an equilibrium solution to systems of this form always at the origin. So that's at 0. So 0 is always an equilibrium solution. To the system. And in particular, if the matrix A is non-singular, this will be the only solution. If, on the other hand, the matrix A has a determinant of 0, which is not something we're going to really encounter in this class, but if that were to happen, then what that would mean is there was actually a whole line's worth of equilibria. But that's a little bit of an exceptional case that we will not really dwell on. All right. So such systems can be analyzed in terms of their eigenvalues and eigenvectors. Now, in the next couple of sections, we will explore the cases of the more exotic types of things that can happen with eigenvalues and eigenvectors, namely complex or repeated eigenvalues / eigenvectors. But for now, we're going to focus primarily on the case of two distinct real eigenvalues. Two distinct real eigenvalues. So, if A has eigenvalues lambda 1 and lambda 2 with associated eigenvectors v1 and v2, then the solutions have the form x of t is equal to c1 e to the lambda 1 t v1 plus c2 e to the lambda 2t v2. So this is all just a recap, really, of what we just saw last section. Now, then, if we untangle what this means, if we assume that the initial conditions are such that this one disappears, and there's going to always be some such initial condition, then what we have over here would just be a line, and similarly over here. So there are two straight line solutions. We can call them x1 of t is equal to just the c1 e to the lambda 1 t v1 and x2, which is the other one, e lambda 2t v2. So these represent straight line solutions, and they are always of the form of lines that are coming into or going into or coming out of the origin. So essentially here, if v1, let's say, looks like this, and let's say v2 looks like this, then we've got a whole line's worth of values here, where essentially we have some initial constant and then we have an exponentially growing or shrinking, depending on the value of lambda, weight on the vector. Now, these solutions will be going into the origin whenever lambda is negative, and they'll be coming out of the origin whenever lambda is positive. When lambda is negative, the solution along the line, let's say lambda 1 or lambda I, along the line that contains vi will go into, or let's say go towards the origin as t goes to infinity, and when lambda I is positive, then the reverse, it will go out of. The solutions will go away from the origin along VI. All right, so that's interesting. Now, the larger of the eigenvalues is called the dominant eigenvalue. And the significance of it is that when t is getting ever more positive, the solution curves will be pulled in the direction of the corresponding eigenvector. When t is negative, they will be pulled in the direction of the other eigenvector. So when t is positive, and large, solution curves they tend to point let's say parallel to, I was going to say the direction of, but that would imply that it goes in or out accordingly. They tend to point parallel to the eigenvector associated with the dominant eigenvalue. When t is negative, solution curves tend to point parallel to the eigenvector associated with the other eigenvalue. All right, so then finally what we can do is characterize the equilibrium based on the behavior of the solution curves. So when both eigenvalues are positive, the origin forms a source. When both eigenvalues are negative, the origin forms a sink. And if it's one of each, when one is positive and one is negative, the origin forms a saddle point. And in the case of a saddle point, we call the line that is associated with the eigenvector, which in turn is associated with the dominant eigenvalue, to be the stable line, or sorry, to be the unstable line, and the other one to be the stable line. So for saddle points, the straight line solution with the positive eigenvalue is the unstable line, and the one with a negative eigenvalue is the stable line. Okay, so that was a lot of text, a lot to write, but let's recap here. So what we have is a situation where we have a matrix. It has two distinct real eigenvalues, and each of them has an eigenvector. The straight line solutions will be lines pointing along the direction of those eigenvectors. If the eigenvalue that goes with that is positive, then it will be pointing, then the solutions will be coming out from the origin. If the eigenvalue is negative, then they will be going in towards the origin. The larger of the eigenvalues is said to be dominant, and the reason why it's called that is that as the values of t get larger, the weights on that particular vector, they overwhelm the weights on the other vector. So the solutions all tend to end up pointing in that direction. Now, when we have two positive eigenvalues, then that means all the solution curves are coming out of the origin, meaning that the origin is a source. If, on the other hand, both eigenvalues are negative, all solution curves are pointing in towards the origin, and so it is a sink. And if it's one of each, then that means the solution curves come in towards the origin along one direction, and leave out from the origin along a different direction, and so it is called a saddle point. And there is a saddle, and the line of the vectors the solutions coming into the origin is the stable line, and the line along which they leave the origin is called the unstable line. Okay, so that was just a recap of that, and now let's just try some examples. Okay, so examples. So what we're going to do now is we're going to come up with 3 examples, one to illustrate essentially each of the phenomena discussed here, and then we'll look at them on Bluffton and confirm that the things that we are producing by hand here correspond in fact to the actual behavior of the solutions for these differential equations. Okay, so here we're just going to say for each linear system dx dt equals ax, we're just going to have some questions. Let's go I. First question, find the eigenvalues. We can't say much until we have eigenvalues. Okay, shoot. What is the dominant eigenvalue? 3. Find the eigenvectors. 4. What are the straight line solutions? 5. Classify. The equilibrium at the origin. And then 6. Sketch the phase plane and several solution curves. Okay, now for the first example here, let's just take A equals, we can just sum it all up by saying what the A is. A equals 6, 14, -4, -9. Okay, so we need to find the eigenvalues first. All right, well, A minus lambda I is just going to be 6 minus lambda 14, -4, -9 minus lambda. And so then the determinant of A minus lambda I would just be 6 minus lambda, -9 minus lambda, minus 14 times -4. Okay, and so what's this going to be? So lambda squared, we're going to have -6 and +9, so it's going to be a total of +3 lambda. And then we're going to have, it looks like, -54. And then on this one, it's going to be plus, so 14 times 4 is 56. Okay, so then what is that going to leave us with? That looks like it is going to be lambda squared plus 3 lambda plus 2. And now I will discretely pretend like this was set equal to 0 the whole time so that I can solve for my lambda. And here I am going to then factor this, and it'll be lambda plus 2 times lambda plus 1, which gives us lambda equals -2, and a lambda equals -1. Okay. So now the greater of the two lambdas is the dominant eigenvalue, which here means we're talking about lambda equals -1. Okay. Now the eigenvectors. So we'll start with lambda equals -1. So then A minus lambda I is just going to be 6 minus -1. That's going to be 7. 14, negative 4, and negative 9 minus negative 1, or in other words, negative 8. And I just go through the usual process here. Choose a row. Now I can multiply everything by 1/7 to get x plus 2y equals 0, x equals negative 2y, and so I can pick x equals negative 2, y equals 1. So my first eigenvector here is going to be negative 2, 1 to go with that eigenvalue. All right, so this is going to be the eigenvector that corresponds with the dominant eigenvalue. So what that means is solution curves will end up pointing in a direction parallel to this. Which just for a note, what direction is that? That's negative on the x, positive on the y, so that's going to be going like this. And if it has a negative scalar in front, it'll be off that way. Okay, so that's the direction that we will expect our solution curves to all end up pointing parallel to. Now, the other eigenvalue, lambda equals negative 2, this will lead us down the same basic process here. We get a minus lambda I. It's going to be 6 minus negative 2 is going to be 8. 14, negative 4, and now negative 9 minus negative 2 is going to be equal to negative 7. Okay, so be it. Then 8, 14, negative 4, negative 7 times x, y equals 0, 0. Just pick one. And here, 8x plus 14y equals 0. Multiply both sides by 1/2. 4x equals negative 7y. Alright, well then I can just choose x equals negative 7, y equals 4, so then v2 would be negative 7, positive 4, which is actually very, very close in direction to the one that we just drew. It's in fact it's a little too close for comfort, frankly. And when it comes to just hand drawing things, it's going to be negative 7 steps on the x, so a little bit less than 2 to 1 on the x and y. So it's going to be ever so slightly steeper than the v1, but very, very subtle difference. Okay, well, so be it. So it's going to have a subtle difference between the two, but that can happen. And then the two straight line solutions. So the two straight line solutions are going to look like, well, one of them, x1, first solution, is just going to be c1 e to the negative t negative 2, 1. The other one is going to be x2 of t is equal to c2 e to the negative 2t, negative 7, and 4. All right, and now the nature of the equilibrium. So because both of these eigenvalues are negative, That implies that the origin is a sink. All of the solution curves will be tending into the origin. And now finally, what's it all going to look like? Okay, now when we are trying to draw this, we have to remember that we are not computers, and so we may need to make certain distortions in order to make things a little bit cleaner for ourselves. So in particular, I might want to exaggerate the difference between the two very close to each other vectors here in order to make it a little bit more visible what's going on. So in particular, if you look at it, this is -2 for x and 1 for y. So if for example we were to plug in, so if we were to make it -8 on x, that would be 2 for y. Be 4 for y. So I'm going to go ahead and I'm going to put 4 for the y, and out here I'm going to exaggerate a little bit the difference between the 7 and the 8. So let's say that's 8, and that's going to be about 4, say right there, 6, and 7. Okay. So for the x1, we are talking about -8, 4, so it's going to be slightly further out. For x2, it's going to be -7, 4. So the x1 here, so the x1 curve is going to be going like this, and it's going to be hard for me to draw here. I'm going to have to make it a little bit slanted. Apologize. We're having some vectorial difficulties with the closeness of these two curves. Computers are a lot less picky about these types of things than we humans are. Now I've really exaggerated the difference out here. This was x2 and this was x1. And this was x2. Okay, now a thing to remember about both of these is they are sinks, which means that they are coming in. They're coming in from both directions here. Now, so basically, whatever the solution curve is, it starts off coming basically parallel to x2, and then what happens is, as t gets bigger, it kind of swings around and ends up trying to be coming in along x1. x1. So it starts off coming in along x2 and sweeps around and tries to come in through x1. So what you get is very close here to a spiraling type thing. You'll see that it's not quite a spiral. So let's see what's going to be happening here. So here it's going to be going like this, and then it's hard to see exactly what's happening in between there. It's too close. Okay, so this one is coming in, and then so it starts off going like this, and then it comes in like that, I guess. And same thing over here. It starts off and then comes in like that, I guess. No. I take it back. What it's going to be doing is going like this, I think. And again, it's very hard to see exactly how these are going to be going. The important thing about it really for us is that it is a sink. A sink. Okay, well, that ended up being a bit of a mess, but don't worry, we'll look at this with Bluffton, and they'll straighten it out for us. The important thing to note is that they are all going in towards the origin. How exactly that gets accomplished is a little hard to see sometimes, but we just have to do the best we can. All right, now let's look over at another example. So another one. Let's say A equals 4, -3, -1, 2. All right, so we just go through all the business, find the eigenvalues to start with. A minus lambda I is 4 minus lambda, -3, -1, 2 minus lambda. The determinant of the same . 4 minus lambda times 2 minus lambda minus -3 times -1. So set this equal to 0. And over here we're going to have lambda squared. On the coefficient side, we're going to have, it looks like, -2 and -4 for -6 lambda. And then number-wise, we've got +8, and this is minus, 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 so it looks like it is a net minus of 3. And so what do we get? We get lambda squared minus 6 lambda plus 5. So then we can factor lambda minus 5, lambda minus 1, which then leads us to lambda equals 5 and 1. So notice already we can see these are both positive. So our mind is reeling with the possibilities here. All right, so the dominant. The dominant one is lambda equals 5. So that will dictate the direction the solution curves will all end up pointing, given enough time. All right, eigenvectors. Eigenvectors. So first off, let's start with lambda equals 5, the dominant one. So then A minus lambda I. So we can just look up here, put in 5 for lambda. We'll have -1, -3, -1, -3. And so what we're going to have then is -1, -3, -1, -3 times a mystery combination of x's and y's, make 0, 0. And just take this, and we'll have -x minus 3y equals 0. So -x equals 3y. So we can do x equals 3, y equals -1. So that gives us a v1 of 3, -1. Okay. So be it. So it's positive change in x, negative change in y. So it's going to be going like that way. Okay, lambda equals 1 now, the less dominant of the two. Well, a minus lambda I. We just put in 1 for all the lambdas up here. It's going to be 3, -3. And then it's going to be -1 and 1. All right, so then 3, -3, -1, 1. And I'm just kind of going on autopilot here. You may have noticed that it might have been easier to use the other one. Oh well, I'm just blundering along on autopilot because you don't need to be 100% in the game to execute these maneuvers. You can just kind of go automatically on a couple of the stages of this. Okay, so then that means x minus y equals 0. If I multiply everything by 1/3, that means x equals y. So then x equals 1, y equals 1 would do the trick, meaning v2 is equal to 1, 1. Now that is, of course, going up that way. Okay, so good to know. Good to know. Now what? So now, number 4, we'll look at the straight line solutions. Well, one of them. So one of them is x1 of t is equal to c1 e to the 5t 3 negative 1 x2 of t with c2 e to the t 1 1 5. Classify the equilibrium. Well, they're both positive eigenvalues, and so that means that it is a source. Okay, now we get the fun part. We get to actually sketch the phase plane here. The important thing to remember, well, I guess one of the important things to remember is that all of the solutions here are going to be coming out of the origin. So I'm going to start with the direction indicated by V2. So x2 of t represents solutions along this particular line. The other one, 3 negative 1. 3 negative 1, so it's 3 over negative 1 down. Represents going from here to here. These are all sources, once again. So sources, sources, and this is the dominant source. The dominant source is along this direction. The less dominant source is along this direction, and what that means is that the solutions will start off being parallel to this curve and end up being parallel to this one. So if I have it like this, it's going to be going so essentially all the solution curves here start off there, they're pulled in the direction of here. And depending on where exactly they emerge, could be but they all end up pointing in that direction. And all solution curves are coming out of the origin. They're all initially under the influence of the V2, but as T gets bigger and bigger and bigger, the overwhelming weight on the V1 starts to become more and more dominant, and all curves end up being parallel to the V1. Okay, so there's that. Now, last one here, let's say A equals 1, 3, 1, negative 1. So, for this one, we have to find the eigenvalues. So, A minus lambda I, 1 minus lambda, 3, 1, negative 1 minus lambda. Now, make the determinant of that. So, the determinant of the same is equal to 1 minus lambda times negative 1 minus lambda minus 3. 0 is what we set this equal to, and what do we have? Lambda squared. So we have lambda squared. For the linear term, we have positive lambda minus lambda. So those disappear, and then for the constant, we have negative 1 minus 3. So then this gives us lambda plus 2, lambda minus 2. And so then that gives us lambda equals negative 2 and 2. And that means then that lambda equals 2 is dominant. And then, let's see, what else did we need to find? 3, what are the eigenvectors? Yep, makes sense. Okay, so let's start with lambda equals 2. So A minus lambda I will be 1 minus 2, it's negative 1, 3, 1, negative 1 minus 2, negative 3. So negative 1, 3, 1, negative 3 times xy. Mystery xy. What are they going to be? Let's find out. So negative x plus 3y equals 0. So then if I move it around, 3y equals x, and that means I can use x equals 3, y equals 1. Those would certainly satisfy this equation. And so 3 and 1 for my v1. Lambda equals negative 2, on the other hand, will take me to a minus lambda I equals, now what do we have? 1 minus negative 2. That's going to be 3, 3, 1, and then negative 1 minus negative 2 is going to be 3. Oh, wait, hold on, what am I saying? So negative 2. So 1 minus negative 2 is 3. 3. Negative 1 minus negative 2. All right. Negative 1 minus negative 2. That is 1. Right, there we go. Okay, that makes more sense. Now, pop quiz. How did I know that that couldn't be right? If your eigenvalue is correct, one of the rows must always be a multiple of the other row. If not, you've done something wrong. So I knew that that couldn't be right because that condition was not satisfied. Okay, so 3, 3, 1, 1, xy equals 0, 0. So 3x plus 3y equals 0, x equals negative y. So x equals negative 1, y equals 1 would do it. And let's see here. So the directions here are something like that. More in the x than y. And then this one, negative x, positive y. So going those ways. All right, now let's see. So that was number 3. Number 4, we need some straight line solutions. Now, of our 2 straight line solutions, one of them is stable and the other is unstable. And it all depends on their eigenvalues. So x1, the first straight line solution, is going to be c1 e to the 2t 3, 1. And this is stable. Sorry, unstable, I mean. Unstable because the lambda is positive, meaning that the solutions are coming out from the origin along this vector. C2 equals a negative, C2 e to the negative 2t negative 1, 1. This one is stable. And that's because the eigenvalue is negative, meaning that the vector, that vector is the direction along which they will be going into the origin. All right, and what sort of origin do we have here? So 1 positive and 1 negative. So it's a saddle point. And then for 6, we can try to sketch it. All right, so our unstable. So our unstable line is x1 here, the dominant eigenvector, or sorry, the eigenvector that goes with the dominant eigenvalue. And then we have the other one, x2, for the stable line. So they come in along x2, and they go out in the direction of x1. So what that means is the solution curves go like this. So they come in along x2 and go out along x1. So they are all receding from the origin in the direction of x1, hence it being unstable. They're all coming in towards the origin, though, for at least the first part of their career, along x2. All right, so that's what we say they look like. Now, let's have a look at what Bluffton says and compare notes. All right, here we are. We see a search engine result for Bluffton differential equations. We bring it up. We change it over to system. We get rid of the curve that is already on there and is not relevant to us. And what we want to put in is the system that corresponds to our example A. So if we look at the particulars here, the system that we want needs to have coefficients of 6 and 14 on the x and the y respectively on the first one. And then it needs to have -4, -9 for the x and the y on the second one. Okay, so what do we have going on here? Now this really shows up the sort of pitfalls of trying to do this by hand. What we determined about it was all, in fact, accurate. It's just that it becomes a little bit hard to see the exact details of it in practice here. So it's hard to distinguish exactly what's going on here, but if you look at it, there is a slight difference in the slopes of these solution curves at the beginning and at the end of their careers. And what makes the difference is that when the t is just starting out, it tends to follow along the direction of x2. But then as t gets bigger and bigger and bigger, it ends up along the direction of x3, or sorry, of x1, I should say. So if we put in the actual two curves here, one of them had just slope of -2, so we could just say negative, or I should say, what is it, -1/2. So -1/2 x. So that represents the first one here. Let me clear all my other curves. That represents the x1, and then -4/7x. That represents the other one. So you can see very close to each other, these two lines, and one of them represents the direction of motion when it is when the t is smaller, and then they end up coming in at the direction of the other one. So it's a little, this is the kind of thing that's a little bit hard to have projected on paper, but we did the best we could. Okay, now let's look at example B. So example B. So in example B, we had coefficients on the first row of 4, so that'd be 4x according to this formatting, minus 3y. And then the second one here, we have -1, so -x, plus 2y. Okay, and now let's go ahead and put in these two lines. I like this. So we change this one to be our x1 in this case, which ended up being just 1, 1. So that would be y equals x. Okay, and then for the other one, that one ended up being, that one ended up being, oh, sorry, 1, 1 was x2. So I'm gonna switch these. So it's 3 for x, 1 for y, so that means -1/3. -1/3 is the slope, and then this one can just be x. So we still have the red one for x1 and the green one for x2. Okay. So then let's see what happens in the long run if we start plotting curves on this. So here it was a little bit easier to project what was going to happen. What happens is they all start off going along the direction of the one, and they end up the direction of the other. And because the two were so vastly different from each other, we end up with just this nice little stream of solutions. So every solution curve here starts off its career by trying to be close to the direction of x2, and then as the t gets bigger, it gets overwhelmed by the dominant eigenvalue, and so it gets pulled towards the dominant eigenvector. And that's what happens in this one. Okay, we'll clear that one, and we'll put in finally example C. So for example C, what did we have? We had in the first row 1 and 3, so that means just x plus 3y. And then for the second row, we had 1 and -1, so that means just positive x minus y. And now for our two straight lines, looks like we had for x1, 3 for x, 1 for y, so that means positive 1/3 for the slope. And for the other one, for x2, we had -1, 1, so that's just going to be -1. Okay, and now we can see our saddle point, and you can see that the solution curves, they come in along one direction. They come in along the direction of the subdominant eigenvector, and they go out along the direction of the dominant one. So there's a vector inward and a vector outward that they take. And those are determined by the eigenvectors that correspond to the two eigenvalues. So that's how that goes. All right, so that's a comparison of what our hand-drawn examples, how those meshed with or failed to mesh with what technology gave us. All right, so on that note, let's go ahead and call it a section. So I'll see you for the next one, where we'll look at what happens when the eigenvalues go complex. All right, till then, bye.